Okay, off we go. Last time we were talking about this example right here, and just a reminder, we made a choice about doing the slicing in this order based on the fact that you look at right here at this equation, you see z is best as a function of x and y. I'd rather solve for z than any of the other variables, right? And clearly the better choice. We don't want to introduce square roots when we don't need to, and so that's the choice we're going to make. Now we could switch the dx and the dy. That would be a reasonable option. I'm going to do it in this order. It's going to turn out that it won't matter, but anyway. Okay, so I can conclude from this that this is a reasonable choice for how to think about doing a projection. Now remember, there's a lot to say about what is a good projection, right? What do we mean by a good projection? And the big idea is you want to think about what does the shadow look like, because effectively the shadow is a set that has all the same x and y coordinates, or all the same coordinates of whatever projection you're using as the original solid. And so you can just slice up the shadow instead of slicing up the solid. So clearly you want that shadow to be a desirable shape in some reasonable sense. Okay, and there's also the question of these top and bottom surfaces, and I think this is about where we left off. I don't remember exactly. Anyway, let's go ahead and do this. It might be repetition, could be worse. Okay, so we are going to be doing a projection down into the XY plane. Here's what that shadow looks like. And again, every time you take a slice of this solid, you are effectively also taking a corresponding slice of the shadow. Right? So when it comes to thinking about the x and y, the range of values of x and y, the bounds for your x and y integrals over the solid, you can just look at the shadow. It's just as good and a lot easier to work with. Yes?
When you're working with like a one-sheet or a hyperbolic paraboloid, where is the shadow? Because everything's being covered at that point.
So this is definitely a sometimes kind of a tool.
Okay.
Right? And so there are plenty. We're going to see another example in a couple of minutes here where we're going to see several examples where there would be undesirable projections. And so if stuff doesn't work out nicely, don't do it. Yeah, absolutely. Yeah. Okay. Right. So thinking about now what our shadow looks like, and again, we're interested in the x and y bounds. XY plane shadow, XY bounds. So we're just going to slice up that unit quarter of a unit disk, and that's a 5.2 type question, and I encourage y'all to confirm that y'all can get those bounds right there. Okay, so effectively we have now done the slicing necessary to pick a let's see, what did I decide? dy, right? So we've done y slicing. We've fixed a value of y. We then did x slicing. We've now fixed a value of x, and so in effect we are now looking at that point right there, above which is our slice of our slice. Right? Now we do have to look at the three-dimensional solid. The shadow is not going to tell us what we want for this last part. But I can see what my slice of my slice looks like, and now I just have to think through, how am I going to get this lower bound for z, and how am I going to get that upper bound for z? This is the second part of what makes for a desirable projection. Notice that the first point, as it were, as I move in the z direction on this slice of my slice, that first point, always going to be on this surface. Always the same surface. Always with this equation. Consistently, no matter where this green point is, anywhere in the shadow, looking at the little line segment above that, the slice of the slice above that, the lowest point is always on that one surface. So this is what I mean by the bottom surface being consistent. It's always the same surface that gives you that bottom point that is going to give you your lower bound. Yeah.
I'm a a bit confused. So when we sliced it, the shadow was just this vertical line, like this one. Is it just this?
That's the
slice?
That's a slice of our shadow.
And then how, like the green point, did we just randomly pick like where X and Y would be, and then we saw?
I mean, it's not. I mean, random is kind of the wrong word. Yeah. What we're doing is, I mean, Y is actually going to, over the course of the Y integral, it's going to be all the different values between here and here. Yeah. And for any given value of Y, X will take all of the values between there and there. So when I say, pick a point, all I mean is as a for example. Okay. Right? And now this is eventually going to be all the points in the entire shadow. Okay. But we're just going to look at a for example so that we can see how the geometry works.
And then we integrate it over the whole thing.
Yeah, we'll be integrating over all values of Y and all corresponding values of X. Yeah, right. Okay, so consistent bottom surface. So when I'm looking for this lower bound, as I will be when I'm thinking about Z1, right? The point that gives me that lower bound is always the same surface. It's very convenient. Now, what about the ending value? What's my upper bound for Z going to be? Well, it's always going to come from that point, or a point like that. And again, we have a consistency. That point will always be on that surface with that equation. Consistently, no matter what X and Y are, no matter what this point is down here in this shadow, the upper bound will come from this top point that'll always be on that one surface. So I'm going to come back up here. We have top surface is consistent as well. Okay, so this is another aspect that we can sort of generalize, and I'm going to say this is another aspect of what we mean by a good projection, because that makes it easy to analyze to find your Z1 and your Z2. And again, you can look at the algebra solve for Z in these equations. Let's see here. The lower bound is this Z. Oh, wrong color. This Z right here. Which is right there. Didn't even have to solve for it. That was convenient. The upper bound is going to be this Z. Again, lucky break. Don't even need to solve for it. Won't always get that lucky, of course. And that's your upper bound. So much easier to take this projection point of view on the slicing process than it is to draw the slices themselves. And if you don't believe me, draw that. You can do it, by the way, right? I don't mean that as sarcastically as it sounded. But you are going to find that it's hard to draw, and you're also going to find that the slices of the solid are even harder to draw. And by the way, this is not the worst example. I'm going to show you a truly nasty one in a couple of minutes. Okay, I am a big fan of this projections point of view. Here's another nice example. Now, what I've drawn out here in the notes shows how to do this with the usual slicing method. Our domain is going to be this unit ball, this whole big solid unit ball there. Geometric appeal: if you slice a ball, you will get a disk. And I think that's pretty believable. You get a disk like that for a given value of X. That X slice, you can talk about what do its Z slices look like. Well, a Z slice, okay, art challenge here. Its Z slices would be little line segments like so. All right, and then for a given value of Z, you can talk about, well, what's the smallest value of Y that would come from this point? Give you Y1, and what's your biggest value of Y that would come from this point? That give you your upper bound for Y. So you can do that slicing argument. And again, I went through that quickly, right? But the point here is, notice this is, again, artistically kind of challenging. This is non-trivial. I mean, again, you don't believe me? Give it a try. I think you'll find it's a little bit non-trivial. It's easy to make it look bad. It's hard to make it look kind of decent. Okay. So again, let's see the easier way to do this. What I think is an easier way to do this anyway. And that is to think about, now we've already chosen for whatever reason due to our differentials in this order, dy, dz, dx, let's look at the outside two, let's see, let me make a good color choice here. Our outside two differentials, this suggests that we can think about this instead from the point of view of a projection to the xz plane. Looking at this ball, what is the projection to the xz plane? And, well, that's a pretty easy pitch, I hope. I kind of missed the little thing there. Okay, now again, it's harder to draw than it looks. It's a lot easier to intuit this than to draw it. But the projection, if you were to take this unit ball and just smush it into the xz plane, it's going to make a unit disk in the xz plane. And the unit disk is pretty easy to find the bounds of. And that's a section 5.2 question. Again, make sure to think that through. In fact, you could even draw a corresponding two-dimensional picture of this unit disk in the xz plane. And a lot easier to see it when you draw that two-dimensional picture. And again, these are the bounds. So again, we're 2/3 of the way done. Kind of in a snap. Nice method. Now, those remaining bounds, we're going to again pick some point there, just a for example point in the shadow, in the projection. We're going to think about the range of values of y, the remaining variable. Well, we start at that point. That point is consistently on that surface. Nice and consistent. We're going to be ending at that point. That point is consistently on that surface. So I don't need to draw slices, right? I can just see what the lower bound's going to come from the left surface, the upper bound's going to come from that right surface. And those equations, again, pretty easy to write down. Solve for y. Let's see here. Yeah, solving for y. On the left surface, we get y is that. Right? And solving for y on that surface, we get y is equal to that. So now take your pick, right? You can do the question either way. You can either think of it from a slicing point of view. You can think about it from this projection point of view. I think the latter is easier. That's just an opinion. Okay, how we doing? Okay. All right, let's see another example. This next one is a little bit of a weird one. The art on this. Actually, not even the art. Just the geometry. Just figuring out what this thing looks like is actually kind of challenging. So you're going to notice I have described my surface as being bounded by a collection of 5 planes. And let me just go ahead and confess, in general, if I were to give you 5 random planes, this would be inappropriately difficult. It'd be brutal. I don't even think, I could probably do it, but oh my gosh, it'd be super tedious, and I'd have to consider, you have to worry about all sorts of little ugliness like 2 planes intersect, but then there's another plane, and which side of the intersection of the first 2 planes does the third plane, is it on that side or that side? Just the headaches and the nightmares would be horrendous. Okay, so that is not what this is. This is not 5 random planes. This is a special choice of 5 planes as follows. 3 of them have no y's in the equation. And I'm going to flash y'all back now to chapter 1, somewhere in the middle of chapter 1. We were talking about the equations of lines and planes, and I put up a theorem. It'll come up later. Here we are. We have a theorem that says exactly this. If you have an equation of a plane, if there are no y's in that equation, that plane is parallel to the y-axis. And this is going to be hugely convenient for us as follows. Let's start with, let's say, this line, this plane right here, z equals x. How are we going to understand z equals x? I'm going to start off by just thinking about what that looks like in the xz plane. Just the part in the xz plane. That's all. And inside of the xz plane is just a line. Furthermore, it's an easy line, right? Z equals x, nothing to it. It's like that. Now that was just the intersection with the xz plane. Okay, now what we really want is the entire whole, the whole of z equals x. And the whole of z equals x is parallel to the y-axis. So I know that it's going to kind of go in that direction like so. And so I know that it's going to be kind of vaguely kind of like that. And I like to think of this myself as, you draw the line in the xz plane, and then you just imagine taking that line and just kind of dragging it in the y direction, because in fact your result is parallel to the y-axis. So that's one way to think about it. And again, you can do this for several of these planes. Not hard to see that those three as lines in the xz plane will kind of intersect like this. And then, all right, well, so just kind of drag parallel to the y-axis. And you can probably already kind of see where there's going to be a prism involved in this shape. How we doing? Everybody all right? So, again, every so often this comes up. Every so often it's very handy to use this little trick. No y's in the equation means parallel to the y-axis. Okay. All right, all that remains is a couple of last planes. Y equals 0 is an easy one. That is, in fact, the xz plane itself, and that intersection is clearly a triangle, about like that. The last one, unfortunately, is a little clunky. That it's not parallel to anything. Okay, well, fine, but I can take this equation and I can just plot a few points. What I think is particularly convenient is think about the axis intercepts, which are all 3. Right? And so I know that this intersects on each of the axes at 3. And so, something like this, and now there's no way around it. You have to use your geometric intuition. How does this angled plane, how does that cut through this blue prism here? And geometric appeal is all I can do. And I think it looks something kind of like this. Is that cool? Everybody happy? All right. Okay, one other thing I guess I can point out, and that is that once you've already established that you've got this prism, right? You understand the values of x and z that correspond to those edges, right? And then when you're trying to make sense out of how this plane, how this plane sort of intersects it, you can just plug in, literally one at a time, these values of x and z, and then solve for y, and that'll tell you where those points are. And that might help you draw it. Okay, anyway, there's the picture. Now let's start with the slicing. And how do we want to slice this up? I claim that there is only one good answer. This is a fantastic geometry/art exercise. I want to encourage everybody to do this. Think through all 6 different orders in which you can slice. And what you're going to find is that in 5 of those 6, you will slice through a corner in the middle of your slicing process. And at which point, you reject it as undesirable. So, really good exercise. Give that a try. I'm going to show you one of these attempts. Actually, technically 2. let's think about what would happen if I put dy on the outside. Okay, well, I'm making my y slices. There's my first y slice, and then I continue making more. Okay, try to make these geometrically competent. A bunch of y slices like that. Everything's looking good, and you can probably see this coming. We're going to slice right through that corner. After which my slices change. Now my slices, oh gosh, let's see if I can do this. My slices now oh gosh, kind of like that. So they just don't look like triangles anymore, right? So they're qualitatively different, which means I've got a whole new integral. Okay? The purple region is going to be one integral, and then in this, what I'm going to call the green region, you get a whole new iterated integral because of the different shape of the cross sections. And then you hit this corner, and then there's another whole new shape of cross section that you get there, and the art there is not good. But the point is, you don't really even need to have good pictures of these cross sections, because all we're doing here is rejecting this choice of slicing as clearly undesirable. So the whole point to this is that we're not going to do anything with these slices. They don't slice nicely. Is everybody happy? Okay, so that's 2 of the 6 options down. I'm going to leave 3 of the remaining for y'all to think through on your own. And I'm going to show you the one that works very nicely, and that is this one right here. Your Z slices all look like oh, come on, I can do better than that. Z slices. Let's see, I'm trying to avoid the... Okay, here, let's do it like this. The Z slices all look like this. No problem. No corners except at the very start and the very end, all of which is okay. Let's see, that's the Z slices. And now let's think about what does an X slice of this Z slice look like. Well, the X slices would be line segments kind of going through here like this. And again, no problem, no corners, except at the very start and at the very end. And then Y, for any given value of X and Z, Y goes from the left face to the right face, and we win. Everything's fine. Everybody happy? Okay, now that is geometrically tedious to think through all of the slices and to draw the slices. It's hard, artistically hard. Let's take the projection point of view on this. And I think this one just is easier. There's a personal opinion, right? Everybody's going to have a different take on this. I'm going to think about the shadow. Oh, you know what? Just to mix it up, I'm going to think about the shadow in the YZ plane. The shadow in the YZ plane is going to be something kind of like this. See that? That's the shadow. And now for a given value of, a given value of a pair of values of Y and Z, well, there's going to be a corresponding, come on, I can do better than that. I'm going to try to make your art as decent as possible. There's going to be a starting value of X. It'll come from that point, which will always be on that face. Sounds good so far. But here's the problem. The ending value is going to be on, well, either that face or this face. I don't know. It depends on which green point in the green shadow we look at. And these are 2 separate planes. So I don't have a consistent upper bound point for the x interval. So I think that's a bad choice. That's a bad projection option, and we're not going to do it. Everybody see that? Okay. So what's the good one? Well, there's only a couple other options, and you can think through the third one on your own. I'm going to show you the good one, which is, as I have it drawn here, the shadow is this in the xz plane. If I then look at the corresponding range of values of y, well, the starting value of y will always come from a point like that, which will always be on this face consistently. Good. Right. And the ending value will always come from a point like that, which is always on this face consistently. And that's good. So you get let me get ahead of myself. So the shadow, in fact, I'm just going to use the fact that that's already in gray. The shadow tells you the x and z bounds. That's just slicing up a triangle, no big deal, 5.2 example. Make sure you can do that, of course. And then the lower bound comes from solving for y on the blue face, and the upper bound comes from solving for y on the red face. Much easier, I think, than the slicing. How we doing? Okay, last example. This one really is hard, and I'm not even going to make the attempt at the slicing. It's too hard. I'm not that good with the art. It's just hard. I encourage you to give it a try. I think it's a fun experience of failure, right? So you can see how hard it is. So you can see why you don't want that to be your only method for how to get triple integral bounds. Try to draw, for example, a z slice of that solid. Yes.
Can you scroll back for like one more second?
Okay. Yeah. Yeah, yeah. So give that a try. Try to make a z slice of that solid. Now, I'm not saying you can't do it. I'm just saying it's hard. Right? Okay. All right, so I'm going to take a different point of view. I'm going to think about projections. Oh, by the way, of course, make sure that you're good with understanding what these equations describe by surfaces, and it is these two paraboloids like that. We're looking for what's in between there, and what's bounded in between is also hard to draw. I'm going to kind of say it's this, but it's not. It's more than what I've got shaded here. This is, I like to think of this as like a heavy glass goblet that's been kind of turned on its side, right? And what we're interested in is the glass region itself, if you will, right? And here's the thing, the rim of the glass is over here. So there's glass right there. The problem is, behind the glass, there is a cavity. Behind that, there is more glass. So it's just going to be hard to draw from a shading point of view. And again, not that it can't be done, but it's hard. Okay. Yeah.
Quick question. I know that the shadow exists in the XC plane.
Yep.
But how do you differentiate between putting like DZ first or DX first?
Sometimes it doesn't matter. In this case, it just wouldn't matter.
Oh, okay.
Yeah. So if you see no particular argument one way or the other to favor one or the other of those options, take a pick. Probably doesn't matter.
And it's the same for the previous situation as well?
Nope. For this one, it does matter, right? Because when you're slicing up the shadow here, let me just get rid of the mess. When you're slicing up this shadow, you want to make sure to slice this way, which avoids corners, right? But if you slice the other way,
I see.
You would slice through that corner. So yeah, I'm not saying it never matters. I'm saying in this case, it doesn't matter.
Okay.
Every example is different.
Okay.
Yeah. Okay. All right. So yeah, I don't want to do the slicing method on here. Again, I think it's just artistically too hard. But the shadow method is fine. And by the way, which way you should do the shadow practically leaps off the page at you, because you see it's very desirable to have y as a function of x and z. Again, we don't want square roots. That means you really kind of have to put dy on the inside. Process of elimination, that means x and z are on the outside, and so if anything, we'll be looking at projections in the xz plane. Yeah.
Does it matter if the x comes first or something?
It doesn't in this case, but sometimes it does. For the example, yeah. Right. Yeah. Right. Yeah. In this case, I don't think it matters. Yeah. Okay. So the shadow. Is this back here? Getting a little bit of a geometry problem, not a hard one. That we have a disk shadow there, and for any, and I already have this drawn down here. Let me come to where I've already got this drawn. On that shadow, that makes it messy. For a given point in that shadow, this is how y ranges. And notice the starting point that will determine our y1. That starting point is consistently on that surface. How convenient. And the ending value, the ending point, that'll tell us our y2 is consistently on that surface. So the lower bound surface, the upper bound surface, you solve for y. Solving for y on the blue surface gives us that y is that. And solving for what? Not that you even have to solve. It's already solved for. But just as a point of formality, solving for y on that surface gives you y equals that. And there's your triple integral. Everybody on board? Okay, so there you go. There's endless examples, right? I can't do all of them. I can't even do a representative collection of them. There are too many. But I think the examples that I've got in here hit all of the main concerns and considerations and tools, etc. And so what you need at this point is a lot of practice. Let me emphasize, drawing is another, unavoidable. Annoying, sure, yeah, right, but nevertheless, unavoidably useful skill, critical to communicating your geometric understanding, right? So make sure you're good with the drawing. Again, if my ideas might be helpful, I've got that recording on my YouTube channel. I encourage you to look at the two recordings. I encourage you to look at those. Also, you need to give yourself time to practice that, because it's non-trivial. Yes.
How would you do the DZ slices?
Oh yeah, that's the whole point, is that I don't want to have to think about that, right? So I took the projection point of view, and I found both the x and the z bounds all together by thinking about the shadow in the xz plane. And that's just a disk. You can think about the equation of the bounding circle and take a 5.2 approach to it. Yeah. Yes.
That was my question.
Oh, perfect. Okay. All right, so give yourself plenty of practice on this. By the way, also unavoidable, no getting around this, independent even of the art, is the geometry, right? It's one thing to be able to draw. It's another thing to be able to sort of understand it and think about what the cross-sections look like. That, too, is something that, okay, again, you cannot get around it. By the way, I've seen a lot of students who have had a high school course in multivariable calculus, and their high school teacher told them, oh yeah, when you look at the way a question is phrased, you always, you take the algebra and whatever is here, you put that there in the iterated integral, and yeah, those methods only work in narrow special case circumstances. They will not work in general, and I cite as example of this question. And I ask rhetorically, what is it about the statement of this question here that gives away, without any geometry, that there is only one of 6 possible slicing orders that will actually work? Answer, nothing. There's nothing about this algebra that makes that clear. Right? So any non-geometric argument that you might have seen before, I think is doomed to failure on at least some occasions. And it also is not representative of valid mathematical reasoning correspondingly, and so it's something you just really shouldn't do in this course. Did I see another hand somewhere? No? Okay. All right. So moving along. Section 5.5 is a monster. It's going to take us at least 3 lectures, and we'll see. We have 15 minutes left today. I think it's going to take us the rest of today and probably all of next week, if I had to guess, just to finish section 5.5. I don't know why Kali has this as a single section. Most books have this broken up into 2 sections, both of which are big, by the way, right? So this is like a state of Alaska kind of a deal. Y'all know how big Alaska is? Alaska is so big, people from Alaska like to make the following joke. Texans like to talk about their state as being the biggest state, which it isn't. Of course, Alaska is bigger. And just to show those Texans, Alaska has entertained, they haven't, but we might break Alaska up into 2 states, so Texas will be 3rd. Right? By the way, I'm from Texas. So anyway, 5.5. I don't know why it's all one section, but anyway, here we go. I'm going to start with a reminder. Substitution rule. Y'all all remember substitutions. You might have thought of it as a method. As a method, I'm going to present it here as being an equation. That's if you were to represent substitutions as an equation, this would be it. I hope that looks familiar. Why am I going back to single variable calculus? Well, it's for the same reason that I have on a few other occasions, and that is that if you take just the right point of view on certain single variable concepts, they generalize very nicely in a multivariable setting. And so that's exactly what we're doing here. So in particular, that just so point of view is to think about the substitution rule geometrically. You probably haven't many students have not thought of the substitution rule geometrically. They've thought of it as, algebraically, that's, you take that and you plug that in for the dx, and, then the algebra just kind of works out nicer if you do it like so. All right, so I want to stretch this out and think about this geometrically. X is g of t. You'll notice I'm representing this now where I have the t-axis is my domain and the x-axis is my target. So t is the input, x is the output, and g is the function that takes me from here to there. A couple obvious comments. A goes to g of a. B goes to g of b. Of course it does. Right? Now, less obvious, if I have taken my interval on the t-axis and if I have chopped it up into little sub-intervals, and if I were to look at one of these sub-intervals, like this little sub-interval right there of size dt, you can take all of those points. Just one at a time, plug them into g, see what comes out, and, you get a bunch of points that come out. And, this initial input interval of width dt, the outputs won't necessarily have the same width, because who knows what this g function is doing. It might be weird, right? It's certainly allowed to be weird. It doesn't have, could be anything, right? So this little image subinterval will be a different size from your pre-image subinterval. So if I want to get my hands on how big that is, what is that dx? I'm going to have to understand how much it's been stretched. How much does plugging an interval of points into G, stretch it out and make it bigger. And I have a take on this that I think is particularly nice. This is just, I don't know, I find it intuitively satisfying. I want to think of dx as being some factor times dt. What is that factor? Well, I can think of this size, this is just a take, right? I can think of this size as being a change. I can think of t was here and then I moved over to here. That input change corresponds over here to dx being an output change to size, but I'm also thinking of it as a change. And, well, input changes to output changes. What relates input changes and output changes? The derivative. And so the thing that you multiply by the input size to get the output size, what I like to call the stretching factor, is just the derivative. And so in this single variable context, we have an answer to what that stretching factor is. Is that cool? Everybody happy? All right. Okay, so now, let's suppose we have an integral like this, where the domain is an image interval, right? Keep in mind, g of a to g of b. This is the output interval from this as the input interval. If I have this integral over here on the right-hand side, I can do what I want to call pulling back. And the reason I call this a pullback is because, keep in mind, the function goes that way. You can think of the function as defining forward. Well, what the function does is it takes points on the left and it spits out images on the right. The function's going that way, and we're going to do this kind of backwards sort of a thing where we're going to take an expression that's on the right, and by way of this g function, details to follow, we're going to try to figure out how to take an expression that's on the right and pull it back to produce an expression on the left. So this is a term that is in similar use elsewhere in math. The term is pullback. And I think it's very nice in this context. Okay. So, this is actually pretty straightforward. Go ahead.
My question is, so to go back, we just took the g prime of t dt, which what we got, and why are we multiplying it by f of gt? Like, why is that the multiplication factor to bring it?
So the premise is that we're starting with an integral here, and that integral has some integrand that, I don't know, is what came to us for whatever reason. Yeah. Okay. Right. Yeah, so the process of taking a given existing integral, it's really pretty straightforward because, this x is literally g of t, so just plug that in. No, there's no tricky curves on this part. That's literally just plugging in the formula that we have for x, which is g of t. Stick it in there. And as we just discussed, dx is g prime dt. And as such, every part of this expression on the right we have successfully rewritten in terms of t's. And there's your new integral. Okay, now I know this is a weird take on substitutions, right? But the point here is not to teach you substitutions. The point is to take that certain point of view on substitutions that's going to generalize. Okay, is everybody willing to, however weird this might be, does everybody see this particular angle on? Okay, so let's do that in 2 dimensions now. I'm going to start, for reasons that'll become clear in a minute, with a desirable domain over here. And we're going to plug into some function. It's like this is our substitution function. There will be a corresponding image, and this image over here is going to be wacky because G might be weird. Right, and so even though I had nice straight line, rectangle, straight line edges over there, they might be curved and weird over here. Okay, and now let's suppose that I've got an integral that I want to do on this undesirable domain, right? Very undesirable. I don't want to integrate on this. Think about what would happen if you had to do an integral on this. You're going to be slicing through corners a lot, right? Lots of corners. So this is a highly undesirable integral. I don't want to do this integral. Okay, all we have to do, just kind of mimicking what we did above with substitutions, this particular take on substitutions, let's just do a pullback. Let's just figure out how we can represent, well, let's see here. First of all, the first part of this is easy. If I have x comma y, x comma y are literally the output from the function g. X and y are literally g of uv. Plug it in. Again, no deep water there. That's just you have a formula that says x equals, stick it in there. Is that cool? But we do have this business about stretching, and so just like we saw in the substitution example, there's some little piece of area here, du dv, some little sub-rectangle on the left, and when I look at its image, what does that turn into over here? Well, it's going to be some little piece of area, but it's probably not even going to be a rectangle. It's going to be some weird little shape. You could probably speculate it'll usually be very close to a parallelogram, which it is. That's nice. But still, what's the area of that? What is this, what I'm going to call dA, representing this image area in the xy plane? And the answer is that, well, again, it's going to be, there's going to be some factor, some stretching factor that the execution of this function performs, which is take a little piece of area and stretch it out by some factor to make it a different piece of area. And we're just going to have to figure out what that stretching factor is. And then we can pull back all we want. Does everybody see the strategy? Yeah. So this turns out to be really, 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 really useful and powerful. Now, we got a lot going on here. Left domain, right domain, change of variables function, 4 different variables, 2 different integrals. There's a lot of balls up in the air. There's a whole digression as to how to find the formula for this stretching factor. So rather than muddy the water by going off on some abstract discussion, I just want to tell you what the stretching factor is. We'll come back to why. So just temporarily, I'm going to ask you to take this on faith. Here's what the stretching factor is. Oh gosh. Well, anyway, that's fine. It is the absolute value of the determinant of the derivative matrix of your G. So whatever your change of variables function is, whatever this G function is, this G function, we're going to look at its derivative matrix, take the determinant, take the absolute value. That's what the stretching factor is. And there's an excellent reason for that, and we'll get to that probably next time. So here, a little bit of notation before we wrap it up. Just FYI, don't forget what the derivative matrix is. Of course, it's the matrix of partials. Those partials, of course, are arranged in a very particular way, and that matters. Make sure to get that correct. And then heads up, be advised that the determinant, not the matrix, not the absolute value of the determinant, just the determinant, we shorthand like this. Partial xy, partial uv. It's a very compact way to represent that these are a bunch of partials of x and y with respect to u and v. That's kind of nice. It represents the fact that we're taking the determinant of this matrix, because that determinant's a scalar, so we write it as a scalar. But be advised, it is not a fraction. Partial xy by itself is not a thing. Why do we write it as a fraction? It's because it behaves like a fraction, and we'll pick up there next time. See y'all later. Have a great weekend. Yeah. Don't forget about attendance.